There we go. All right, we're going live now. Take it away, Teamer.
Are we live?
Yes.
Hello, everyone. Welcome to the Audio Programmer Meetup, virtual meetup. Thank you so much for tuning in. My name is Timur. We have a lot of interesting stuff for you tonight. Hello, everyone, and also Josh, my co-host. Hello, Josh. How are you doing tonight?
I'm great, and I'm really excited for this month's meetup. We had a great one last month, and we're shifting gears into two more technical talks with three DSP experts. So I'm really excited about this. And before we get started, I want to give a big thanks to our sponsors, Juice, Sonics, and Focusrite. So thank you for helping to make the Audio Programmer Meetup possible. And we are really excited to be here. And we have some great guests with us. We have Stein and Priscilla from TENERS, which stands for
This is not rocket science.
Yeah. This is not rocket science, and you will memorize that by the end of the meetup, I promise. And we also have Garrett Luff from right down the street from me, over in sunny for now, Cambridge. How's it going, Garrett? Say something to us.
Yeah, how are you?
All good. Hey, all good. Great. Cool. So we're going to, is there anything else you want to talk about, Teamer? You want to talk about ADC?
I just want to quickly mention ADC, the Audio Developer Conference. You can find all the information about that on the website audio.dev. And the Audio Developer Conference is taking place on the 15th and 16th of November, and it's going to be simultaneously on site in London and also online. So you can either join us in London or you can enjoy ADC from the comfort of your own home. I want to thank this month everyone who submitted a talk. We had a lot of submissions. We had actually 51 submissions this year, which is, I think, 16 submissions more than we had last year, which is quite fantastic. So, and also the quality of these submissions is really, really good. Right now, you can actually vote on the talk, so you can let us know which ones you like most, and then those are the ones that are going to get into the program, because obviously we have way more good submissions than we actually can accept. So it's going to be tough, obviously, to pick the ones that are going to make it, but I'm sure at the end we're going to have an amazing program. So just thank you everyone who submitted the talk. I think soon we're going to be able to release the first tickets, and you can join us, as I said, either on site or online, and I think it's going to be amazing. As I said, you can't submit any talks to ADC anymore because the submission deadline is already over. We're already reviewing the submissions that we got. But if you want to talk, if you want to give a talk, a presentation, you cannot submit to ADC anymore, but you can submit to this very meetup because it's taking place every month at the second Tuesday of the month. So to do that, please go to audioprogrammer.com/submit. Yes. And then let us know what you want to talk about, and we will be delighted to have you on the show. With that being said, let's move on to our first presentation or our first session tonight. Unless there's anything else, Josh, from your side?
No.
All right.
Like we said, we were really excited about the submissions that we've seen for ADC. Looks to be another strong conference this year. Once tickets are out, I encourage you to please come and hang out with us at the conference. It's a great opportunity to meet other people who are into audio programming and who are also trying to learn more about audio programming. So yeah, please join us. Hope to see you in November.
All right. Okay, so for our first session tonight, we have Stein and Priscilla Haring-Kuipers. I hope I pronounced it more or less correctly. They are together running a company called This Is Not Rocket Science, as we already mentioned a bit earlier. And This Is Not Rocket Science actually is making hardware, as we can already see in a second. So Stein and Priscilla, hello. Thank you very much for being on the show. Please tell us a little bit about yourselves and what you do and what is this hardware is all about.
Well, this is not rocket science. Well, it comes from the idea that everything is easy once you know how to do it. And that is usually our approach to things, you know, do your homework, figure things out, but then just get to doing it, which is very much hardware thing. Reality is the biggest check of if you got everything or not, because it is brutal.
Yeah.
Um,
We've had a particularly rough manufacturing day today, so our minds are still a bit blah. This is rocket science. We try and make things that are easy. Well, it's sort of not easy to learn, hard to master, that kind of stuff. It tries to get out of your way. So whatever you're doing, it's not actually that difficult. You want to make people feel good. You want to make things sound nice. We don't try to make tools that try to be important by themselves. They should enable somebody to achieve a goal. And if that means we have to go all out rainbow puke to make people sort of feel that it's not so serious and they're allowed to touch it and things are color grouping or whatever, then we'll just go all out rainbow puke. Where other manufacturers might choose black because it's the safe color or whatever. But I think nobody feels helped by black, and we try to make things that people want to use. So that's another core part of why it isn't rocket science.
and you've been programming.
I've been programming in general since I think I wanted to be a programmer since I was 3 years old. I didn't become a programmer until I was about 10. And then one of the first things I tried to do was get a computer to make sound. I mean, the first day the computer came into our house, I was sleeping with the programming manual under my pillow and trying to sort of figure out how to get this thing to go beep. And then by the time I was a bit older and I really wanted to make house music, which was then the thing you got on a cassette tape, bootleg tape from somewhere, I was completely enchanted by it. So I went into the studio store with my saved up pocket money, only to find out that you needed a substantial investment of gear before you could make anything decent. So I went home and I did the proverbial back of the envelope calculation to see if the computer I had at home could theoretically do it. And it turned out it could. And so I had to learn how to program well enough to get the beeps out. And then a few decades later, I'm here.
In between have been a lot of plugins.
Lots of plugins.
Soft synths.
I started out in Trackerland, like Fast Tracker and earlier, and then a lot of Jescula Buzz. I think I did about 70 plugins for Jescula Buzz. I did a bunch of BST plugins. I made a complete software modular synthesizer for educational use, and then another version of it for more studio use. Then I did a lot of game audio engines. I taught game audio engine design at Media Technology School and audio design in general. So been all over the place. And in between that, I've been employed as a freelance inventor to actually make enough money to afford my audio dreams. That's that's been a rocky road. But since a few years, we've gone full time. This isn't rocket science. This is now the only thing we're still doing. We started out small because after all these years of audio development, of course, the software bit was, well, it's still not easy, but it's trivial compared to everything else. So I found out that for about €1 worth of chips, you can have something that can run a monosynth. So I said, well, I just buy the chip, I put it on a board, I learn how to program that. I have the code from some ancient Pocket PC plugin I wrote, I just copy paste it in. And that seemed feasible as a road in. So we designed a tiny synthesizer box, and we took this box to Shenzhen to figure out, okay, we know if you want to make hardware, you produce this in China, but we have no clue where this process goes or where how to go about it.
Can we do this?
Can we do this?
And we wanted to step into this with an actual, or at least actual enough product to make.
Yeah.
So that's where we started. This is not rocket science. My background is absolutely not in programming or DSP, but in marketing, social sciences, media psychology. So the only programming I know is statistical packages to do the analysis of experiments with, which is not what we're doing anymore.
No.
But it made a very good team to hold a company. And it also means that we, I guess by my social background, constantly are asking ourselves also more the philosophical and social questions. Why do we do this? What do we want to experience? What do we want other people to experience? How do we facilitate? And you just said, like, we don't want the things, instruments to be in your way. We want the, the best UX is the UX you can't see, that you forget. But we do have opinions, obviously, about color, as you can see here, about playfulness, about openness. Everything we do is open source. The whole "this is not rocket science" thing is usually also a collaboration. So there's another designer behind this, which is not in our company, but works with us. There for other modules, there are other designers behind it that work with us on that project. Yeah, so that's the "this is not rocket science" part. And look it up online, this is not rocket science.nl, because hey, we're Dutch, so and there's a lot of dev blogs that were just rambling on how does everything go with production this week. We try to be very open about everything, not so much as a shining example, but more as information of,
Here be dragons, warning.
This is what might happen. This might be a good idea. This might not be a good idea. No.
But we went to China with our simple box, which turned out to be kind of a complicated box. So came back home, simplified stuff, go to the literal minimum viable product. Like, where do we feel that we know enough about software that it makes sense to put it in a hardware box without making the hardware too difficult? And the first thing we did, which also fits the rest of the design philosophy of the thing, was a procedural melody generator. Because if you're any familiar with these massive boxes of synthesizers, if you are live on stage and you're there's a crowd in front of you, they're waiting, you have a beat going maybe, just having something safe to just plug back in. So I don't know what to do, let's give it a procedural melody that's sort of in the right vibe, and it will just do the thing while I set up the next sound. So we looked at a whole bunch of procedural melody generation, and we looked at things like Markov chains and deep learning, and eventually I think I found our guru's old Psycho sort of Windows standalone melody generator things. And then we just sat down with a clipboard and just said, well, this baseline, if a note goes up, they'll make a thing go up. If make a checkbox go up, goes down 2 notes later, got a whole statistical grid of all the standard musical styles that were there, made a statistical generator that could actually make the same style happen again, and put it on a tiny chip. And then we just designed the whole product range for our first hardware release around that. So the code for that was very pragmatic, very simple. There is no memory in the chip. It's 4 kilobytes of RAM total, 24 kilobytes of flash space for your entire program, which includes all the drivers and the bootloaders and everything else. So a very simple, tiny bunch of algorithms worth having, and we grew our first product around this. And then I'm not sure how familiar people are with the development of circuit boards. It's like a 2D graphics package. You have a whole bunch of components, and you draw lines between the components where you want them connected until at some point, I can close up. This is a more recent design, but yeah,
it's a very simple one.
This is a very simple design. But then you get into the cycle, just like building software. Instead of the build cycle with hardware, is you press go, and then you send out a whole bunch of files to a whole flock of different factories. And maybe 2 weeks later, you start having enough components to manually assemble one prototype, which can take well, initially it took about a week to assemble a prototype. These days it's sort of one hand you solder one prototype, with the other hand you're making soup. We're getting faster there. Hey. But this whole the design iteration speed of you think of something, you design the thing, you press go, and 2 or 3 weeks later you see, well, no, this is not what I meant. So you just throw it away again, you start drawing again, you wait another 3 weeks, and then you have your second version in hand. And again, as a contrast to programming, these iterations are not free. So some of these prototypes, depending on what you're doing, are rather expensive. So this pressing go becomes like, do I really dare to press the button now? Because if I get it wrong, it's yet another expense. So also time and expenses, and also waste of material and logistics and everything involved, because there's so much stuff being put in motion by the time you're actually pressing go.
But the first thing that you mentioned before, procedural sequencer, is called Tuesday.
Yeah.
But DSP in Tuesday.
No, there's no DSP in Tuesday. Not yet. We're getting there. We're getting there. Because we're still ramping up. I mean, before you can actually do anything sensible, you have to have all your building bricks in place before you can have a complicated enough thing together that actually works, that you can sort of be creative with it, because the technology has become trivial. So we're still building towards a level of triviality that we can go back to designing a thing that's worth having. And in the initial, the Tuesday procedural sequencer, the building of the mount is, not sure, maybe open question. Can that be considered DSP, or is that
what?
There's no signal flowing through, there's just a pattern being generated?
It's not a signal, a pattern.
Yeah, I don't know. Edge case.
What do you think?
Is this signal
it's an edge case? It's an edge case to me. Yeah.
DSP or not?
Yeah, I don't know. It's just too low speed.
Okay.
But by the time we got this trick ready, like we have the whole pipeline set up, we have all the factories mapped out. We are now quite comfortable with pressing the order button. That was the first time that this is rocket science could really say, well, now we're going to take one step back and see how we can finally apply our thoughts on things. And now we're also going more to the core of why we're here, and what already earlier discussed with Joshua. The reason why you build a DSP system is usually that you want to enable somebody to do something cool that you would probably personally like to experience while you're on the dance floor. I want to make the ultimate knob that somebody will drop that beat with, that I will go completely apeshit when I see somebody do that. And a lot of the DSP stuff that I see is more focused on how can we get this sawtooth perfectly band limited. And when I'm on the dance floor, I don't give a shit. So how can we make a control where I enable that thing that I want to happen all the way at the consumer end of the process? So like with the Tuesday, I want that modular live performer to have something to fall back on, so the vibe is not gone. So what can I help them with? Well, I can give them melodies that are always good within a certain style, and I can just press the button and forget about it or rely on it even. And same with like an oscillator. You can say, well, I can make a perfect sawtooth and it will be exquisite in its edginess, and it will sound pure all the way up to bats falling out of the sky. But if I'm going to do the research into what sawtooths people would actually like on a dance floor, they would do something completely different. For instance, the classic example of this is, of course, the 303 sawtooth, one of the most popular ones ever made. If you look at it on an oscilloscope, it isn't. It really isn't. is some sort of shark tooth with ringing edges and a filter that craps out. Yeah, that's completely different goal. So as soon as you start from the goal and work backwards, and you say, well, okay, apparently I need this completely wobbly thing that makes my hairs go up. How about I just put my hairs up first and reason backwards? So it's from that perspective, we started well, not with an oscillator. That's a whole different story. There's a bunch of cool stuff in the Phoenix that we have here that we'll talk about later. The wobbler. Okay. I have here the wobbler. It's actually
you talk about it.
World primer. This is the wobbler 2 already. But the wobbler is an LFO that does what I want an LFO to do, and that in this case, what usually you have a piece of music and you think this is boring, so I want an LFO. This is maybe a weird approach, but usually you have some sort of you are too lazy to draw an automation track. Is maybe a better conclusion. So instead of drawing an automation track, I'm going to enable something that does this for me, that will do it interestingly enough, so I don't have to. And if you then go one step further, like I would actually want to draw this automation track, but I would like to copy me, there's another copy, and say, well, me, can you make my ideal automation track for me? No, I couldn't, of course. I didn't have enough memory inside these devices to make any decent attempt at a copy of myself. So then we start asking, well, what would I ask a potential band member to do for me? Like Steve, the operator of the cutoff knob. Steve, can you wobble it slightly for me? You know, that way that I like. And then I started sort of pulling apart the exact vocabulary I might want to use to convince Steve to do the right thing for me. And then because you're live on stage and music is loud, you can barely talk to each other. You may sort of end up with 3 hand signals, faster, slower, you know, a bit more that way, and something like that. And these hand wavings have now been converted into 3 knobs on this device. We have the speed, of course. Well, 4 knobs actually. The speed, well, okay. We have a shape knob, which is a bit ominous because it doesn't have the usual shapes. It has a phase knob because sometimes we'll change the timing a bit, and it has a modification knob. But all of these are a completely gradual field of modulations that are non-stepped. So where in some systems you might select between I want a triangle LFO, or I want a saw LFO, or a sine LFO. Everything here is a smooth interpolation between everything. So you can have a sine and it goes slightly more triangle-ish, and a triangle goes slightly more saw-ish, and then there's saw morphs into a pulse and all the way and back. But that's only the first shape. That's sort of a modification of first shape. Because from there, if I would ask myself to control this knob, I would not do a sine wave. That's boring. You do something else. You want to dance with this knob. You don't want to do the regular thing because that's.
So, if I could ask, it sounds like you've put a lot of your personal judgment and your feeling of grooviness into this object. You said that also a lot of this is open source.
Yes.
Like how much of these decisions you've made, which are kind of capturing a lot of the personality of your product, end up being public?
All of them.
All of them. Did you feel any awkwardness or pressure around that? Because I've heard from people who make hardware that I went to a talk by someone who made a little JavaScript board, and they said that they could sell the hardware and that was fine.
Yeah.
But they tried to keep the software closed source and they got literal hate mail. So like people really expect this kind of, they expect to be able to open source everything. So I was kind of wondering if that's something that you encountered or whether that's like just aligns with your values anyway.
No, everything we do is open. Well, for more than one reason.
Yeah, you have a very morbid one.
Yeah, the morbid one, but also the nice one.
The nice one is more the philosophy of learning, which is very, very important to both of us. And is you have barely any formal education. So what you know from the internet and the kindness and openness of others. To how can we then now not share and do the same? And again, it is not to be a shining example of this is how you do it, but it's just this is how we did it. And if this is helpful to you, then awesome.
Yeah.
And there are now a couple, I don't know, is it a couple hundred? The Choose DIY group.
Choose DIY Facebook group.
So there are a bunch of people who are making not just the Tuesday, the Wobbler, other modules that we've made too.
All the hardware itself is also on GitHub, and the software and everything. So people are downloading it themselves. They send it to the factories themselves, and they flash them themselves, and they.
So we don't sell kits. We sell like completely finished and tested products that we understand. Okay, this is what we're shipping out, and we can fully stand behind that. And but they build their own version of it just by the schematics and everything, except for the graphics. That's the only thing that we keep to ourselves is the exact front, so that there also shouldn't be any misunderstanding on who made this thing. And mostly this goes perfectly fine. Like people make their own version, they make their own graphics on it. It's an exploration of them of how to build this. People make their own adaptations, which is nice. But we now have, for the first time, also somebody who has made kits out of our designs and schematics, and designed his own fronts for it. And the store who's going to be selling those emailed us first and saying, are you really okay with this? This guy told us that you're fine with this, but are you really okay with this? And we said, yeah, as long as it's clear that our name is not on it.
We don't support
any of this.
If it explodes, that's your problem.
Sorry. And that's fine. But the other way around, I have never felt pressured to be open source, because in modular, a lot of it is not. So it's quite common to not be this open.
Right.
And I have the morbid reason. I don't think it's actually that morbid. But we try and make these things to be not throwaway ever. So like any musical instrument, nobody has ever recycled a Stradivarius as an extreme example. But if I close the source for this and the chip melts, and 50 years from now that chip is not available, but another chip is, then I have no problem with somebody compiling the same source code for whatever ARM 128-bit exists by then and keep it alive. And if it's closed source, it's just dead. So just from a longevity standpoint, I think we have to be open source.
We have an issue with the big thing, because that on not all of it on the inside is ours, and unfortunately, therefore, it cannot be completely open source. Otherwise, it would, but we don't like have the rights to all the schematics in there. So we can't. But this another morbid. This person who's a bit older than us has promised to give us those rights, like in his last will and testament. So as soon as the whole thing will be open source.
but yeah, so I hope that answered that.
So we have another question. We have another question, which is from Once I Had a Cat, and they ask, are you building all the modules all alone? How do you deal with the stress level? There was a person from orthogonal devices who talked about the stress levels due to the high demand.
Oh yeah, demand we don't care so much about.
Well, you don't get I talk to
you talk to the customer. I don't get to talk to the people. Yeah.
We like the high demand.
Yeah, we make what we make and it sells out. It's okay. We don't feel pressured into doing more production runs if we just don't feel like it.
No.
So that's we build what we can build. With the current product, we've been developing this thing for 3 years full time with you and me full time pretty much, and an extra developer, Laudi, also full time. Lately full time. Yeah.
Sometimes part-time.
But we've really gotten into the point where it should have been done by now, but the amount of setbacks we've had has sort of pushed it on and on and on, and we've only been able to deliver the first 25 so far out of the 100 we intend to make. That stress level, yeah, but it's more the stress of not being allowed to be creative because you're bound by the product that you've designed literally years ago, and we're still making it. I want to do something else but it's, yeah. So the stress for the production less so, but the creative limitations more.
No, we feel the stress of the production as well. Like when we said before, when we started the stream, today is actually being really hard day manufacturing wise, as we had some more setbacks and all, like the thing where you expect, okay, we're good now. All the electronics for all the rest of the hundreds they're all in our house.
Tested, fine.
Tested, it's all fantastic. So the complicated part is done. And now we've having issue upon issue with the aluminum cases that they go in. And we cannot produce any further because of our case manufacturer. It's like,
so there's always such a focus on the difficult bit that the easy bit turns out to be the biggest problem.
That bites me
That's maybe it's universal rule of engineering, that the easy thing turns out to be, yeah. It's like the simple questions are always the hardest to answer. So
how do we deal with the stress? How does anyone deal with stress? For me lately, I've been really hanging on to some time away that we've planned when this should be done. But what really helps is to share this with people, because thankfully we have some very enthusiastic customers, and what they make with it is often something we really like. And this, you're building stuff for music. It's not hard to be happy about this. You're making other people happy with this. So that, and connecting back to that when it's really difficult, that really helps. Yeah.
So yay. And any other
Amazing.
open questions? Or is it, or shall I finish the story of the knob? Because there's more to it.
Yeah, I was going to say, just going back to what you were saying about the LFO and your thought process, your creative process around that. Do you think that the industry needs more of that in terms of creative approaches that are breaking the norm, approaches that are making a statement rather than
well, yes,
all too square?
Because these days, technically, the technology to do practically everything is almost free. I've made a point of it we make music as well. Of course, we make instruments, but we make it because we like to make music. And every year for New Year's Eve, we make a countdown track for a trance party. That's I always forget to make music, but the countdown track is sort of the staple that has to happen. But for the past few years, I've made a point of it to just go dumpster diving and grab a PC from the trash and make the track with that, just to show that it can be done. Using freeware and a free computer, just go. And so technology is practically free. The algorithms to do practically everything are also free. So now we get into the point of the theater design, of putting a musician into a good vibe and in an interesting surrounding to perform best. So yet another thing that tries to simulate the hardware look of a Jupiter 80 or whatever. Let's not talk about the cloning or just everybody trying to imitate the hardware. Just give me an interesting musical interaction with the system that takes me places where I didn't expect to go. That seems to be much more rewarding than enabling people to do exactly what's already been done, but now with a different skin on it. So I'm not sure if that's a norm breaking. Yeah, maybe. But it's enabling people to confront themselves in different ways. if that makes sense. And maybe
Yeah, absolutely.
to surprise other people in different ways. Because to finish the one knob, because if there's one topic I want to have discussed, it is one storyline. There's of course the classic knob that goes to 11 from the Spinal Tap, and of course I'm highly convinced that every knob should go to 11, preferably also to I and -1 if you can afford to. But it does mean that you have to sort of look at anything and say, well, what does it actually mean to go slightly further than what my usual numerical maximum is? Like a lot of knobs are pure in a sense, in that they control one thing. But if you have like a cutoff knob and you open it up and the low pass filter is entirely open, that also you can also just go a bit further and do a high boost, just add something completely new in, just to add that extra kick to get the last 10% of range, give it something interesting. So for this LFO, we made the shape. I'm holding it again. In the middle, those 5 LEDs around the tiny knob, around here. Those are all the shapes, and they tell a tiny story, and they go from simple to complex, to even more complex, to chaotic, to noise, and then beyond noise, they go into structured noise. So there's this, you ask somebody to do a regular thing, and then, yes, it's regular, but can you now do a slightly more complicated regular thing? And then it goes into a physical model of what the twang is. Like if you have a stick on the edge of a tail, you go, which is also a perfectly valid LFO, just you give it a kick, and then it starts twanging. And of course, if you can have a twang, you can also have an inverted twang. So there's the modification of where you can make it inverted, so you go and the other way around. And beyond that, it goes into double pendulum, which is the same as a twang, except now it can become chaotic, and you get an amount of chaos tweaking, so you can decide how unpredictable you want it to be. And then beyond that, you get the classic sample and hold noise LFO, and then quantize that again. So you have this whole storyline in one knob, which is again what I said with the hand signs towards Steve. Like, can you make it slightly more chaotic? Can you, or maybe hold it down a bit? And this one knob gives you the entire spectrum of kinds of things that I would expect him to do for me. So that's pretty much the way we try to design all our knobs, if we have the luxury of spending the time on it, because for this particular module, we had the hardware done. It was just sitting in a box, all the modules packaged, ready, except the firmware. And it was like, I think we spent half a year of refining it and tweaking the storyline so it really made sense before I finally flashed the final firmware on them and sent them out. So, okay, this is good, now it can go. But it's yeah, it has been worth it. As in, I've now been playing it with it for years, and I still haven't really wanted to ask this thing anything else yet, except for when we are now releasing version 2. But that's a whole different story.
I have another question. So, have you ever thought about just going back to software, remaking these in plugins or as their own standalone audio applications? Have you ever thought about that? And what would the challenges be to actually creating that?
Well, no challenge at all, because I simulate this all as software already. And my primary background is software, decades of writing stuff. I'm not looking forward to testing everywhere again, because at some point, I think I stopped releasing plugins when there was this explosion in all the different SIMD architectures, where SSE2, SSE3, SSE4, SSE 4.2, there was just no more single target to optimize for, and it would just be fine. Suddenly there was this gigantic mess of targets that all had to work equally well, or you get CPU wars on the forums. So a lot of this we could just do as software, but an LFO as a plugin doesn't really make sense right now. I do have plugins for stuff like our synthesizer voice work, and I have the modular synthesizer plugins that we are going to revisit, and that's maybe big announcement that we're after this thing is done. I'll be working on a keyboard, a synthesizer keyboard, and inside this keyboard we put a modular synthesizer, but a polyphonic software modular synthesizer, and an HDMI out, so you can just have a big screen and a mouse and a keyboard attached. I can just edit the thing without having an operating system or having a remote plugin. But the development environment for this is going to be on the thing and on PC, and that is also going to be all open source. So we are going back into software mode on our own hardware platform, but it's supported by the big, also the PC version.
To skate around the fact that otherwise you don't know what you're programming for or to, so you can't optimize.
Yeah, so then we have one big optimization target, and if somebody else wants to optimize it for something else, then of course they can. But hopefully they'll just want to be on our hardware platform too.
So,
but that's years away.
I actually also have a question, if I may. So it's not directly about your products actually, but it's more like about this theme of learning and sharing that you kind of mentioned before. Let's say I am a software developer who knows DSP, knows how to program in C and C++, knows how to make a software plugin. But now I'm curious about making hardware. You know, I've never done this before, but I'm curious about how to develop a piece of hardware. Do you have any advice how to get into this world, basically? Where to look, where to start learning about like embedded and, things like that?
The simple thing these days, there's a bunch of amazing microcontrollers available for very little money. Like a Teensy is a very nice one. Teensy 4 is powerful enough that you have a lot of CPU power to run your usual synthesis algorithms or effect algorithms. And there are some audio boards available. You have this. I have a tiny board here. This looks almost like it. This is our own thing. So just a board like this with a big USB plug. You can just plug it in, and then you stick it on a tiny audio daughter board, and you can just get started. Maybe you can set it up in like 10 minutes these days, and open an audio example and have it running, and you go.
I think if you're like completely unfamiliar with electronics, get some kits. Get out of the idea that that you are not allowed to break things, that this is somehow very, very difficult, that this is done by people in clean rooms in white coats, because it is most definitely not. And all the hardware in your life has an amazing amount of hands-on. Even Apple, how it produces stuff, still goes through a lot of mostly Chinese female hands in its production process. So this could be your hands too. And if you screw something up, well, either order a new one or desolder it and resolder something new on it. So I think my biggest advice would be
burn your fingers.
Yeah, burn your fingers. find something, and usually these things start with make a LED blink. That is the first step into electronics. Usually, is to make something.
I mean, we have barely touched our show and tell stuff here. Recently, Raspberry.
It's supposed to talk about DSP.
Yeah. But, recently, Raspberry has released their new RP2040 chip.
Yes.
And they have a tiny board based on the chip, the Pico, the Raspberry Pico. That's $4. So
it is amazing. The documentation around it is fantastic. We expect the whole, how do you say that, ecology around this to grow and to be awesome.
But most importantly, it's fast enough. It doesn't have a floating point unit, so you need to be either conservative in your floating point usage because it will be emulated. It will work, it will just be slow, or you can do a fixed point DSP and it will just go blazing fast. It's a dual core 130 megahertz chip for 50 cents, $4 for the board. So you can, in this case, I made a 16 voice polysynth on one of those chips. It runs. So for $4, you can get started in your own hardware development and run some code on there. And there's amazing tutorials on their site on how to actually connect this up and have a debugger running. If you're familiar with GDB, it's all there. Visual Studio Code and GDB and C++. If you're already familiar with those, you can do this.
Amazing. Going back to what you were saying about the teensy, did you have a particular model in mind? Somebody was asking on the chat.
The 4 is where the hardware starts being seriously beefy, but the 3.2 is what you're more commonly what you can more commonly get in microcontrollers, because if you want to make your own board later, not with a TNC, and you want to just put your own chip on a PCB, then the technology that's in the 4 is a bit much more difficult to hand solder. So then initially, if you want to have easy prototyping, take a 4, but if you want to develop for something mass marketed, maybe go for 3.2 or for a Pico. So that's
great. And where can people find your the source code? So you were saying your code is open source. Where will people find
GitHub, GitHub, This is not rocket science.
Yeah.
It's also on thisisnotrocketscience.nl. There's a GitHub link somewhere.
Right. And I'll put the video. I'll put the link in the description as well.
For people that are interested, a lot of our source code is not just this. We also make all the manufacturing tools available. Like this factory panel that I have here. Well, there's a whole bunch of graphics on there. But this panel is automatically generated from a single PCB file, and then it combines it into 5 and makes a frame around it and labels it all correctly. So stuff like that is the whole interface. How we deal with factories, we also share. And all our factory tools go into the repository, and other people can use those too. Because yeah, for things like the big one here, maybe it's finally time to get it a bit closer to the camera.
Yeah. You're lifting it up.
Can we put it somewhere?
Here?
Here, yes. And module, yay. So many things, here's an ending. So, do I still fit in the frame somewhere? No.
No.
Here. So, this is the Phoenix 4. We have been, we spent about 3 years developing this thing. To make something this big is actually kind of a challenge for most design software, because you have to have a PCB that is this size to actually get it together. And there's about 4,500 components in one of these, and most of these design software suites are not created for anything of this scale. So that just frame rate goes to 1, and you sort of have to stop designing because it doesn't work. So a big part of our process to make this thing was to make the build pipeline to actually combine all these things together, and then merge this into one monster design, and then split the monster design back into individual mini pieces that actually fit into the assembly robots. Because maybe you can see there's some cutting lines where the boards split up, because that's the maximum size that one of the assembly robots will take. So the whole build pipeline to make small designs, combine them into a bigger design, then split them up again into designs that can be done by manufacturing robots, then slicing of the design so it can actually procedurally generate all the graphics on here. So all the graphics on here are automatically generated as vector graphics from the circuit board directly. So we have some annotated knobs, like this knob says cutoff, so please add the label cutoff and a nice gradation around it where the circuit board actually is. So that's we try and build this entire pipeline in a way that we can do this, because otherwise this would be way too big for me to design. I may be handy with design software. I'm not that handy. So anytime I can offload anything to the computer for me, we build a script and we try to replace that bit of me with that.
If you replace yourself twiddling the knob.
Yeah, just like I replace myself twiddling the knob, I also replace myself designing circuit boards if I can. So just anytime I can be lazy, I'll spend a lot of time trying to become more lazy.
That's programmers.
It's just But that's general programming, I guess. But yeah, maybe
this is fantastic. I think our audience. I don't see any other questions from our audience. Is there anything else that you would like to share with us? So once again, can you just give us the website, and I'll put the website in the chat as well. So is it it's tinrs.nl, right?
No, the full name. This is not rocket science.nl.
Okay, great.
Yes.
Oh yeah, we have more, of course. Tons more. There's another one massive pet peeve I need to mention. Can we finally be done with ADSRs?
What is it that you don't like about ADSRs?
Yes, everybody bites. It was a very useful abstraction at the point where electronics were barely able to do anything, and these days it feels like such a crutch, because if you're playing the instrument yourself, you're playing a violin, or you're playing a piano, or you do whatever, trumpet, vocals, you don't have ADSR. Usually you try to achieve something like maybe a certain loudness, so you go there, ha, and then you overshoot, which you get into the decay, and then you try to hold on, which is your sustained time, ha, and then you run out of breath and you cut down. But during the process, all your overcompensations and all your interactions with your plan are much more detailed than an ADSR will ever give you. It's way too perfect. But these days we can do more in, like, even if you have something like a spring follower that just like an undampened spring, which would sort of get you the ripple on everything, that will give you a more natural envelope than an ADSR, because you're asking your synthesizer to perform something for you. Again, you're asking yourself playing trumpet to play this trumpet note for you. And depending on the skill level of you, you're going to hit that volume in one go, perfect, no decay, or you're a bit wobbly and you're making it work anyway, or you never reach it at all. So, and that, if I was going to be redesigning my next envelope, I would try and add a skill level, like an intention and a skill level, and maybe an amount of ego. Like, how much of a prima donna is this envelope? Is it going to add the wobble at the end of the note because that just wants more attention? It's just, if you have to build this in a synthesizer and you have only a basic envelope to start with, then you end up having to decorate every note with your automation tracks in your DAW. But you could also just make the envelope a bit more deep or more temperamental, chaotic. No, just give it personality.
Yeah, it's interesting. Like, I'm beginning to understand that, like, you have a whole philosophy behind your approach. Like, it's not just like a way to do like a particular thing, like a, like an LFO, but it's actually like a philosophy that kind of permeates kind of all the different things you do. That's really interesting. Thank you.
Chaos.
So yeah, more chaos.
It's the fight between math and chaos that results in music.
Yeah, kind of go back to like performing, basically. Go back to like the human imperfection of, the delivery.
Or even an adjustable amount of perfection. What does it mean to go hyper perfect? I don't know. But first you need to have this scale before you can go to the other side of it.
Auto-tune to 11.
Yeah, auto-tune to 11 is just monotune.
Yeah, that's did things we weren't expecting, and we don't agree on whether or not we like it.
Yeah.
So
but let's go there first and then determine if we like it.
I love it. That's awesome. So, yes. Anything else you'd like to mention, Stein, Priscilla?
I don't know. Yeah, we're of course we're still.
I love
manufacturing this thing. I advise people to look into it and the whole history. We haven't even had time to really talk about this.
about the Phoenix.
Yeah.
Yeah,
there's a whole history of things.
You said that also. The Tuesday is not DSP.
Yeah, well,
the
of course, yeah.
is an envelope, so you don't want to talk about that.
No, that's how I got envelopes wrong. That's I feel remorse. This is not how you should do it. We took it out of production.
We didn't take it out of production.
did.
We don't produce anymore.
Exactly.
That is different.
In the case of a system like this, we have an analog digital hybrid because again, with digital signal processing, though there's a whole range of analog to digital signal processing, you can go full analog, you can go full digital, you can go fly-by-wire analog, where you digitally compensate for things that go wrong in the analog domain. You can also do analogly digital, which is a bit of a weird one, but you can have non-clocked logic performing digital operations. So we have, in the Phoenix, we've pretty much used every permutation of analog and digital processing that can be thought of, as far as I'm aware.
That you think of. You and
Yeah.
Laurie,
Yeah,
what you thought was interesting, important, useful.
yeah. Also, that's maybe a different kind of optimization that might be nice to mention. That a lot of, well, almost everything we have on this machine could be done digitally, but for some functions, it just becomes prohibitive to do it digitally, and it adds delay. Because this is a completely analog patch bay, and every time you have to have a buffer to take in some samples and then process it and then buffer it out again, that can add up to a millisecond if you're unlucky. Most of our stuff is a bit faster than that, but still, if you have a complex patch, you can the milliseconds start adding up, and it just becomes less interactive or less snappy. So for some stuff like a filter, perfect digital filters exist. We have a really nice digital filter, but in terms of hardware costs, an analog filter is just cheaper. And if it does the same thing, then why don't we do the calculations analog? And if you go into electronics building, then if you can have any mathematical expression, you can pretty much just convert that one-to-one into an electronic schematic. And after a few basic pointers, you can sort of read an analog schematic as just as a chain of operations to a signal and some feedback paths and some, well, it looks remarkably like the mathematics for any signal processing, really, but then in schematic form, and then if you just solder them to the board, they work. That's just with the magic of the internet and fallstat.com. There's an online circuit simulator. You can really just design something on your screen in a simulated environment and then transfer it to a circuit board, and it works first go, maybe with some tweaks here and there, but it's a very interactive and modern experience by now.
So it's physics doing your DSP.
Yeah. ASP, analog signal processing.
Yeah, I love it. Great. So I think that that's it for this presentation. Thank you very much for your time and your perspectives. I think that's been very eye-opening for a lot of people, I think. Hey. And yeah, really awesome. Yeah, once again, check it out. Check out their site. This is not rocketscience.nl for the Netherlands. That's where they're repping today. And they also have a GitHub as well, where all of their code is open source. And yeah, any other links that you'd like to plug?
We're on Instagram. Also, I think it's RocketNut on Instagram. We're on Twitter, on Facebook, we're on the places. Yeah.
Yeah. Right. Oh, and come visit us at Super Booth. We'll be at Super Booth.
Yes. If you
yes.
Also
I'll try to, if they let me into the country, I'll try to come down for Super Booth as well.
Yay.
Yes.
Yeah. So
great. Well, thank you for your time. If you wanted to get in touch with Stein, you can find him on our Audio Programmer Discord. His name is not Stein on the Audio Programmer Discord. It's ZFOD, so Z.
Yeah, it's my old Just Club Buzz nickname, where I released all my older plugins on.
Yeah, it says ZEPHOD. And you can join our Audio Programmer Discord on theaudioprogrammer.com/community. Also, if you'd like to present your work, share your work with us, and show other audio programmers what you're up to, feel free to submit a presentation for one of our meetups. And you can do that on the audioprogrammer.com/submit. And anything you'd like to add, Timur, before we jump into the next talk?
No, I think we're good. I think we can move on to the next one.
Great. So our next presenter is going to show us how to write a reverb. And this is Geraint Luff, who is right down the street from me in Cambridge. And we've worked together quite a few times now. And he's a longtime DSP engineer and also the big boss at Signalsmith Audio. So he's CEO, CTO, and coding monkey. Is that how you described it?
Yeah, that's fair. Yeah.
So for people who are just getting started and want to learn how to write their first reverb, this is the presentation for you. So I will let you take it from here, Geraint.
Cool. Yeah, so I'll just share my screen so that you can all see what I'm about. Come on. There we are. Is that working?
Yes, it is.
Great.
And also,
All right.
before you start talking, everyone on the chat who is following us, if you have a question for Geraint, please feel free to ask it on the YouTube chat, and we are going to ask them here live.
Yeah, and if I start not making sense, Timur, please interrupt me, because I don't want to talk for 25 minutes and then have to go back and
Will do.
Turns out I've been talking nonsense. So yeah, hello. I'm Geraint. I'm Signalsmith on various forums and the Audio Programmer Discord. And as Josh said, I run Signalsmith Audio with my partner. We're developing some like audio plugin stuff, sort of VST3s, but we're also doing a lot of I guess freelance audio algorithm design and implementation, which is really good fun. And yeah, so today I'm here to talk about reverb. Reverb's one of my favorite effects, and particularly feedback delay networks are, I think, a great way to play around and try some weird things. And this presentation, there's not going to be code, really. This is all sort of the design stuff. And we're going through one possible design, which I think is very friendly, as in it's easy to configure correctly and get a good sound out of it. And it sort of sidesteps, I hope, some of the common reverb design problems, which can give it a reputation of being tricky. But I think we can make something, and it's quite straightforward. So yeah, let's get to it. So first off, what is a reverb and what do we want it to do? So artificial reverberation is quite a wide field, and it covers a lot of different use cases. So we're going to take a pretty simple definition. A reverb creates a sense of space by generating a diffuse, long-lasting sound from a short input. Hopefully that makes sense. And there are a couple of ways to achieve this. One's convolution, and the other is, another common one is feedback delay networks. They both have their advantages and disadvantages. We're going to go the feedback delay route because you can get a decent sounding reverb with very low CPU and a pretty simple design. So here is a feedback loop. The input is sent through a delay, and then the delayed signal heads to the output, but it's also fed back into the delay input. So this means that the signal travels around in a loop, and it produces a series of echoes from a single input pulse. And there are a few variations on this, like where in the loop we take the output from, where the gain is, but this essential part, this feedback, which produces an infinitely looping series of echoes, and the gain is in here, which makes it decay over time. So now let's look at a multi-channel version of the same loop. Oh, sorry, I forgot to have audio examples. Here we've taken a pulse and we've just put it through the system, and you can hear it produces a very regular series of echoes. So now this is a multi-channel version of the same loop. I could draw out, 4 parallel feedback loops. Here, I've just drawn double borders to say this is a multi-channel operation, and I've used colors. So yeah, the important thing to note here is that in this multi-channel feedback loop, each channel gets delayed by a different amount. So each channel produces a sort of independent echo pattern. Each channel is regular, but together they produce a slightly more chaotic and unpredictable result. So we can have a listen to that, and it goes like this. So it's slightly more irregular. That more complex sound is good for the kind of reverb that we want, because we don't want these regular juddering patterns. But in this loop that we have here, each channel only repeats its own echoes. So could we get an even more complex result if instead of just picking up their own echoes, each channel starts picking up echoes from the other channels? We can achieve this with a mixing matrix. This is an n by n orthogonal matrix, where n is the number of channels. A matrix being orthogonal, it means it preserves the input and output energy. So in this context, what it means is, as the signal goes around the loop, the energy can never go out of control. So being orthogonal means it's always kept in check. But as you can see, the more times it goes round, because there's this cross-pollination between the channels, the result starts getting more and more dense and chaotic. And so if we have a listen to that. So the tail end of that, if you just give that another go, it's starting to sound a little bit like a reverb, right? Hold on, because at this point, it's very tempting to mix the channels together as much as possible and put a bunch of other stuff inside the feedback loop to try and speed up diffusion. And there are some well-known designs like the ring and Totoro's figure of 8 and so on, which can be understood as instances of this feedback loop. And they work. They often require careful tuning. And, as well as finding a good compromise for delay times, if you use too much inter-channel mixing, it can kind of lock the delays together. And that ends up not being good for the longer tail. In technical terms, if you have too much mixing, it moves the eigentones of your reverb closer together, and this leaves gaps which color the sound. But basically, designing a loop like this to produce a diffuse, long-lasting sound with no strong resonances in it is difficult. This is a hard problem. We don't have to do it. So there were two properties we said we wanted from our reverb. We wanted it diffuse and long-lasting. And even the basic feedback loop that we had earlier handles this long-lasting part quite nicely. The echoes carry on forever. They're not very dense, but they're there. So rather than trying to tune this feedback loop so it also produces a diffuse sound, in our design, we're going to separate the two concerns. So first, we take our input, and then we make a diffuse version of the input. And then we put that pre-diffused input into the feedback loop so that it echoes and reverberates and lasts. If this diffuser does its job well, we shouldn't need to build up echo density in the feedback loop. It can just repeat the sounds. Echo density is the number of echoes you have per second. And when you get between like 2,000 to 4,000 echoes per second, it starts to blend into this continuous diffuse sound that we want. So now we come to what I think is the big problem in algorithmic reverb design, which is you need a really good diffuser. So we want our diffuser to smudge the sound sort of in time without adding too much of its own timbre. And a useful concept here is the all-pass filter. All-pass filters have a flat frequency response. This means that whatever frequencies you put in the input, those same frequencies have the same energy in the output. The phase response gets messed up, which means some frequencies are delayed more than others, which is how the smudging happens. But what we have here is a Schroeder all pass. This is a classic for sort of reverb diffusion basic tool. It's got a single channel feedback loop and an extra feed forward part, which gives it this flat frequency response. Yeah, for the technically minded, here we can see impulse response at the top, and in blue, if you can see blue, there's that flat frequency response and this very wibbly phase response going on at the bottom. So for a reverb diffuser, the delay time in the middle here is typically, it's set to like a handful of milliseconds. So one all pass on its own doesn't provide much diffusion. You can put a bunch of them in a row, and the result is definitely diffuse. It does have a slight metallic edge to it, which is sort of the bane of these algorithmic reverb designs. So if you, all these audio examples, this presentation is going to be also in blog post form, so you can go back and listen to things and tell me if I'm lying to you. Yeah, so there's a slight metallic edge when you listen to this carefully. And if you actually want a kind of digital plate style reverb, this is a classic method to get it. You can make more sophisticated all passes if you replace the inner delay with another all pass. And you can make second order things and cascade them, and they improve the sound by creating a more irregular phase response. There are good designs here for diffusers, again, but choosing one of these designs or understanding why a particular all-pass structure is good, I don't find that very intuitive. It becomes another tricky tuning problem where you're choosing the delays and the feedback amounts, and then the all-pass structure itself, where you kind of stuff it inside itself and combine it in various ways. So I'm not actually very much a fan of these. Things get a bit more varied if we look at a multi-channel all-pass. So a multi-channel diffuser. First, we need to define what that actually means. So the idea of a flat frequency response, we have our input signal, output signal with the same energies in it. That's good. Let's phrase it slightly differently. So we'll say the total energy of the output must match the total energy of the input. So the sound comes in, but that sound might come out at a different time or in a different channel, but all the energy in the sound is preserved. The reason I'm talking about this is compared to the single channel case, we have a slightly wider range of basic building blocks available to us. So let's look at some examples. Much like, you could just have a single channel delay, you can have a multi-channel delay. And this is more interesting because the different channels can be delayed by different amounts. And specifically for our diffuser, if you have some echoes coming in to your multi-channel delay, then this can kind of desynchronize them so that the echoes are all at different times in the result. Another type of all pass, which only makes sense for the multi-channel case, is a mixing matrix. So we mentioned this briefly above, which is earlier. And yeah, so we treat each set of input samples as a vector. We apply this orthogonal energy preserving matrix, which is exactly what we need. And each output channel is a linear combination of the input channels. So this means that, if an echo only appears in one channel, this mixing matrix spreads it out amongst all the channels again. The Hadamard family of matrices, it's just a very good mixing amount. It does as much mixing as it's possible to do, and it can be done pretty efficiently. I'm going to link some example code for just a couple of useful bits like the Hadamard matrix on the blog post, so you can check that out and just copy it if you feel like it. And yeah, so just another thing we can do, it's not very interesting, but if you take your input channels and you swap them around, you just shuffle them, that's an all pass. What the energy coming in is the same as the energy coming out. And you can invert the polarities on some of them. And there are loads more, right? There's a recursive all passes. So there's the Gezon, which is like it's like a multi-channel version of the Schroeder that we saw earlier. You can apply the single channel ones to the individual channels, or do things to some channels, not others. The thing I want to kind of emphasize here is that in the single channel case, when we're building a diffuser, these recursive IIR all passes are the only tool that we have. And you have to stuff them inside each other in complicated structures to get good results, basically. In the multi-channel case, we listed some basic building blocks, which none of them have feedback. They're all passes, but they're all finite, contained all passes. And from just the 3 examples that we mentioned, you can make a good diffuser, which is exactly what we're going to do. So here's the plan. We define a diffusion step, which is made from a sequence of multi-channel operations, a multi-channel delay, and then we shuffle some channels and invert some polarities. And these delays and the shuffling and the inversion can be just randomly picked. And then we put it through a mixing matrix. So from left to right, you can see we've got our multi-channel input. We do a multi-channel delay, so the different channels are now unaligned. Then after some shuffling, we put it through a mixing matrix. If an echo comes in, we unalign the echoes, and then the Hadamard matrix produces more echoes by spreading the new times across all the channels. So let's look at that animation again. Aligned, unaligned echoes, some shuffling, and then more echoes than we started with. So each time you put this multi-channel signal through a step like this, the number of echoes you have in it increases by a factor of n. So for here, it would be 4. For a larger number, like 8 channels, you can get a really dense diffuse result by putting a pretty small number of these diffusion steps together in a series. So let's listen to some examples. This is a 4-channel diffuser, as in the diagrams, and 3 diffusion steps. And each diffusion step is 60 milliseconds long. So the delays in the delay step are between 0 and 60 milliseconds. So, and it sounds like this. Again, it's a little rough. To get a smoother diffusion, you can add more steps, more diffusion steps, or increase the number of channels. Here's an 8-channel, 4-step diffuser. So, I mean, this is what happens when you put a click through it. You get this pretty good hiss, kind of burst of noise sound, which is kind of what you end up wanting for a reverb. You want it to turn a short sound into a diffuse sound. And yeah, you still need to choose the number of channels and diffusion steps, but by just repeating these diffusion steps, you can get a pretty good configuration and a good diffuse sound out of this pattern really easily. And there are obvious controls for just make this better, make it more diffuse. So a couple of things to note. We've created a multi-channel signal, and at some point you're going to have to mix this back down into a mono stereo output. The moment you do this mixing, it's not technically an all pass anymore. It's still a diffuser, and it's not actually a problem to kind of mix it back down, as long as there aren't any regular patterns in your phase response, because you'll hear those patterns when it's kind of collapsed back down. But this isn't a problem for us, because we're just going to be piping this multi-channel diffuse signal straight into our feedback loop. But I just felt I had to mention it.
Can I ask you a question right there? Yes.
Yeah.
So something that I was kind of a bit confused by at the very beginning, like, how do you split a signal into channels? Is it just, do you just copy them? Is it certain frequency bands, or what is it?
You can just duplicate it. So if you've got like 1 or 2 channels of input and you're operating with 10 channels or something internally, you can just repeat it 4 times. You could do left, right, mono stereo, or whatever it is. But honestly, this is a pretty robust design. So you take one channel and you somehow make 8 channels out of it. And then from there, use your diffusion. And the specifics of how you do that are actually not as important as you might think.
Thanks. That clarifies it. Yeah. Thank you.
Great, cool. Thanks for asking. That means you're listening. Yes. I always worry that I talk too fast and everyone just nods their heads. He's off in one of his rants again. So another little detail that's just kind of worth mentioning. I said that the delay times in this, this diffusion step could be chosen randomly. That is one way to do it. Another neat trick, though, is if you divide your range that you want, say 40 milliseconds here, and you divide it up into equal segments, and then each channel's delay comes from a different segment, then your multi-channel delay ends up kind of evenly distributed, but still random and not correlated enough to produce a identifiable timbre. This is similar if anyone's familiar with the velvet noise kind of reverb pattern. This is the same kind of logic, but this is for a multi-channel case instead of a single channel. And another thing, I've accidentally opened a link, there we are. Another thing to note is there's no reason that our diffusion steps have to be the same size. So you could have some shorter steps and some longer steps. To show the difference, we're going to do a really long diffuser. So this is an 8-channel diffuser, 5 steps as in the diagram, and they're all 300 milliseconds long. So this is a really long diffusion, if you can hear that. So that's from a click. That's our diffuser working pretty well. Here's the same setup, but with varying. So the first diffusion step's 48, then the next is 96, and they're all double the previous length. And it sounds like this instead. The difference is really subtle, and again, you might want to go through and listen to the audio examples on the blog post to make sure that I'm not lying to you, but basically it has a slightly faster attack, so it gets going more quickly and less of a peak in the middle. But I mean, as I said, the small decisions like this, there's still stuff you can polish, icing on the cake. But fundamentally, both of these diffusers sound pretty good. And you can get a great sound out of this design almost whatever decisions you make, which is kind of the goal of what I was going for here. And yeah, that is kind of it. So we have our multi-channel diffuser, and then we have a multi-channel feedback loop. And all we have to do is put them together. So from left to right, we take our input, we can just duplicate it to get, say, 8 channels. And then we put it through a series of diffusion steps. So multi-channel delay, shuffle a bit, Hadamard matrix. Delay, shuffle, Hadamard. Delay, shuffle, Hadamard. We've now got a multi-channel diffuse sound. And then we put this straight into our feedback loop. You might notice that I've put a householder matrix. I have used a mixing matrix here. I would recommend householder because it's super cheap to compute and it doesn't provide too much mixing, right? We don't want too much because the diffuser should be doing the diffusing. This is just making the sound carry on. Yeah. And again, at the end, you mix back down to mono or stereo. Just, however, have a go. Let's have a listen to see how this works. So we're going to use a pretty long configuration. So that's 8 channels, 4 diffusion steps, as in the picture here, with that doubling pattern that we mentioned. Pretty high feedback gain. So that's about 1.5 dB reduced each time it goes through the loop. And delays 100 to 200. And here's what happens when you put a little click through it. So I think that's a pretty smooth reverb sound from hopefully a design that makes sense, where you've got your diffusion, which is unaligning any echoes and then respreading them, and then unlining, and then spreading, and then unlining and spreading to create this diffuse sound. Let's try it with some more musical inputs. So here is a bit of funky drumming. And then we put that through the reverb. I hope this is coming over on Zoom. Yeah, here's a bit of gentle piano. Ooh. Yeah, and then through the reverb. There's a slight resonance, but it's actually in the original recording, not the reverb. The reverb it's resonance free. Yeah, so that's it. This is a pretty minimal reverb design, and there are a couple of ways that you might want to extend it. And I'm not going to do a massive deep dive into all the detail, but just sketch out a couple of things that you might want to add. So firstly, the delays in the feedback loop mean that you get some original sound that's probably coming through some dry path that we haven't put on the diagram. And these delays in the feedback loop mean that there's a gap before the first echoes appear in the wet reverb signal. To bridge this gap, you can pluck out the diffused signal from any stage and just do another little multi-tap that fills the gap between the first echoes that come through the feedback loop. So the earliest echo in the loop here, in our examples, was 100 milliseconds. So these could just be like a multi-channel delay between 0 and 100. And that gives you a nice, fills the sound straight away. Another thing that is really common in real spaces is that just tiny movements in the environment. So even like air currents, they produce subtle variations in the delay time of the space. And in feedback-based reverbs like this, we can model this by just gently modulating delay times. Or we can crank it way past realism and to get this supernaturally thick sound. There are a couple of places you might want to do this. You could modulate in the diffuser, and this will give you a kind of like a fixed amount of detuning, kind of like a chorus. Or you can modulate the delays in the feedback loop, and this means the detuning builds up and builds on itself over time, and that sounds really cool. It's worth noting that the moment you start modulating these delay times, you suddenly have to do fractional delays, which is a small amount of extra CPU. Any delay you're not modulating can and should be rounded to the nearest sample. And it doesn't matter if they're like aligned or whatever. We haven't made sure our delays are prime. We've just thrown a random number generator all this. Just don't worry about it. And one more thing which happens a lot in real spaces is high frequencies die away faster. Just most surfaces absorb high frequencies more. We can achieve this in a feedback-based reverb by putting filters in the feedback loop. So the gain here in the feedback loop is what determines how long the decay of the reverb lasts. So if you put a shelving filter in there, you can create a frequency-dependent gain. So our example had 1.5 dB of decay every time it went around the loop. If we added a high shelf with another 1.5 reduction, then the high frequencies would die away twice as fast. And that gives us slightly more natural sound. Yeah, and I mean, that's just the basics, but from there you can add all sorts of weird things. These basic things are enough to get a really good sound. So here's just an example that's piano, a bit of synth bass, and then just the reverb. So it sounds like this. Yeah, so I think that's got a nice sound, smooth decay, good thick sound from the detuning. yeah, that's it. Hopefully this wasn't too complicated, and hopefully that made sense. I really wanted to give this presentation because a lot of the feedback delay reverb designs that you see out there, they've got magic numbers in them, some of them, or you've got these all-pass structures that are kind of nested, and you're like, they feel like they've been very carefully tuned, and I don't think I could have come up with them. And it's not super obvious why they work. And I didn't like this at all. So one day, Josh asked me to write a reverb with just no specifics, just, write a reverb. And I sketched out this design, which had no feedback or no IIR all passes. It's an FIR, a finite diffuser. And the design's robust enough that you can throw a random number generator, add all the delay times and the shuffling and so on, and it sounds good. It's a very robust design, I think, for making a reliably good reverb. This is a distilled version of that design, and I hope that this can be a useful starting point for people to just get going with reverb and then try a bunch of really weird things and then send them to me. I want to hear your weird sounds. Yeah. Are there any questions?
Yes, there are quite a few, just a couple of questions here.
Great.
So Sudara is asking, they're interested to hear what types of algorithms you're excited about these days, like probably beyond reverbs as well.
Beyond reverbs?
Things, or maybe like,
yeah,
like the things that you haven't talked about, but like anything you're excited about.
Well, non-linear stuff is always cool. Particularly at the moment, I've been working on some fun things that do frequency shifts, but not non-uniform. So it's not like shifting up, it's not shifting down, it's kind of just like making it a bit wrong. That's kind of fun. And I'm into, I've been writing a synthesizer, and there are some interesting like user interface problems where the answer, well, at least when I answer them, the answer has a lot of maths in it. Yeah, those are the kind of things I'm thinking about at the moment.
Cool, thank you. There's a question from Mike Boyenga. They're asking, do you have any rules or guidelines for picking delay times for the COM filters or any of the delays, shuffling, mixing, and a diffuser?
Right. So in the diffuser, you can pick them randomly and it works. That thing where you divide it up into equal segments and then pick randomly from within that segment is, extra good. Try anything. It's good. Like there's no need to make things align. The delays in here, in the feedback loop bit, I think they're random in the example. I've tried random. I've tried like exponentially distributed. It's all good because all the channels are like different versions of diffused signals. They tend to not interfere unless you've literally made them like all multiples of each other. So just random, try random, and then try exponential, and then give it a go.
So finally, there's one question by Wave Morpher. It's about the Soul reverb example. I'm not sure if you're familiar with Soul, but in case you are, it sounds like it might be using a similar algorithm to what you're using. Do you have any opinion on that?
I've no idea. That'd be cool. Okay. I've tried to find like a good description of this diffuser, where it's this delay and then Hadamard, where it's all finite and no recursion in the diffuser. If you've got something I can link to, so that I'm not just so it sounds like I know what I'm talking about, and I'm not the only person who's come up with a weird solution to this. Great, yeah, credit where credit's due if I'm not the first to do this, which I probably am not. Yeah, I haven't seen the reverb for the example for Soul, but sure.
All right, cool. And we have one more question actually from Phil Nock, who's asking, how do you compute the RT60 time for an algorithmic reverb like this?
Sure.
And also, can I ask, another question on top of that. What is the RT60 time? Because I've not heard that term before.
RT60 is the number of seconds that a reverb takes to die away to 60 dB down from the original. So you clap or stick a pulse through it, and then if you wait 10 seconds, if that's your RT60, then it'll be that's how much it'll die away. The way you calculate that is, say your RT60 that you want is 10 seconds. I think reverbs are often specified as RT20, which is the same thing for 20 dB. You say, how many times will the sound go through the loop in that time? So if your delay is 100 to 200 milliseconds, you might say, that's about 150. So divide 10 seconds by 150. That's how many loops you have in 10 seconds. And then you say, well, it's gone round, what that'd be, about 60 times. And I want it to die away 60 dB in 10 seconds. So I need to do 1 dB of decreasing by each round the loop. Does that make sense?
Yeah, that makes a lot of sense, actually.
Yeah, with the filtering that I mentioned to get the high damping, you can specify that decay rate for the low frequencies and the high frequencies separately, and then you just make sure that gain curve that you create with that filter matches that, and then you can craft your high and low decay times.
All right. I think Stein had a question as well. Are you still on the call here? Hello?
Yeah, I'm here.
Yeah. Hi.
Well, not so much as a question, but for people that want to explore reverbs, Melda Productions has made a very nice domain-specific language to experiment with reverb algorithms in their M Turbo Reverb. Beside it being a nice plugin, they have also made a very nice YouTube series of how exactly all these L passes contribute to a proper diffuse tail and everything. So that those might be worth checking out. A very nice visual debugger too, so I can really see the quality of your tail, how it evolved if you change the algorithms.
Cool.
All right. And then we have one more question from the chat by Josep. How would you adjust the amount of diffusion in that design?
So you can increase or decrease the number of diffusion steps. So if you want more echo density, then you can just add more of them. So you pick some total amount of diffusion you want. Say your echoes are, in this example, 100 to 200 milliseconds. You might want 100 milliseconds of diffusion. And you just kind of say, oh, well, I'm going to do that as a 25 and a 50 and then a 12 and a something. So the diffusion adds up, and you add more stages for a denser one. And presumably fewer channels internally. You could use 4 instead of 8. 8 is kind of what I'd recommend for like a solid result. Does that answer the question? Was that the question?
Yeah, I think it does, yes. Okay, well then I don't think we have more questions on the chat. So the only thing I wanted to add is thank you so much for this fantastic presentation. It was very clear, very engaging. Like I learned a lot. I wish everyone would just explain their DSP designs in such clarity. So I think really, really, really well done. Thank you so much. I think I learned a lot, and I hope everyone else out there did too. So yeah, definitely. Actually, yeah, there's one question I have, I guess. You don't have a version of this somewhere like available open source or something like that, do you?
Not currently. I'm working on a version because I've created a version of this for a few different situations, but I was hoping to write one which is basically example code, so that I can, with this presentation, you can then see every step that I've made as code, but not currently.
But I think actually, if you are really into this kind of stuff and you want to learn, you could go in and code it yourself. And I think you kind of outlined it to a sufficient detail that I think people could actually play around with that stuff. So
that's the dream.
Yeah, that's really cool. Well, I don't see any more questions on the chat. So thank you so much. I'll give the mic back to Josh.
Yeah, thank you so much, Grant. This is so many people are giving their positive feedback about your presentation, and this is really awesome. And thank you once again, Stein and Priscilla. This is really fun. This is a lot of fun, and I really appreciate you sharing your views. And I think that people have found it very inspiring for their designs. I know I have. Yes, thank you very much. So, thank you as well to our sponsors, Juice, Focusrite, and Sonux for their support for the meetup. And once again, if you'd like to make a presentation, it doesn't need to be as polished as Garrett's and not as experienced as Stein and Priscilla's. Even if it's your first time giving a presentation, even if you're in university and you are creating your first Reverb and you want to share some code and show what you've made, please feel free to submit a presentation, and you can do that at theaudioprogrammer.com/submit. And you can also join our community on Discord. Both Stein and Garrett are on the Discord, and Teamer is actually on there as well. I think he's still in there.
Yes, I am.
So, yeah.
Well, I don't regularly open it like every day, but if you tag me with my name, I think it's Timur Audio or something, then I will respond. So you can summon me by just tagging me in there somehow.
Yeah. So this is really fun. And yeah, the audio programmer community on Discord is a really good place for people to connect of all different experience levels. And yeah, I'm really thankful for people that are more experienced for joining and sharing their knowledge and sharing their ideas with others. And I think it's really awesome. So I'm feeling very privileged. Yes. So yes, anything else, Timur, before we sign off?
Yeah, a couple things. First of all, someone is asking me on the chat whether that is a tree house that I'm sitting in. And no, it's not. It's almost. It's a cabin in the forest. So it's not on top of a tree, but there are lots of trees around. I'm currently in Finland in the countryside, and it's like a kind of cabin in the woods. And the other thing is I wanted to mention is that we are having this meetup every month, which also includes next month. So maybe we should just kind of quickly mention that the next audio program meetup is going to happen, as always, on the second Tuesday of the month in September, which will be on the 14th of September next month. So we're going to see you next on the 14th of September. And I think we don't now have announced any speakers yet. So I think there's even time to submit if you want to talk about something next month, isn't there, Josh?
Absolutely. Yes, we need 2 speakers for our meetup next month. So please feel free, and don't force me to go scrambling like a week before the before the meetup to find presenters. So yeah. So hope to see some presentations. And yeah, if there's nothing else, then I think it's a good time for us to sign off.
Yeah, I think so too. Thank you very much, everyone.
Yes, thank you, everybody. Have a great evening or a great afternoon, wherever you may be. And we will see you soon.
See you next month. Bye.
Great.